All right, guys, so let's get started. So, hope you're all doing well. This is the last tutorial. I know it's very sad, bittersweet, but it's okay, because we're going to make it one of the best tutorials we have, okay? Some other stuff. I'm going to see if I can get, like some movement for some review session. No promises, but if I can't, then I'm going to try and do something like the first step, like record a couple videos, just for extra help. But at the very least, I'll send some extra practice problems which are designed to be understanding based as opposed to just like test questions. So hopefully those will help. But I'll see what else I can do as we prepare for the final. So I'll try my best to get everything that I can out for you guys. All right. I also do have candy canes today. If I owe you like a treat from some other class beforehand, please come up and grab one. Sometime during the class or before I run off to the last one. Any questions before we get started today? All right, well let's do it. So today we're going to be talking about simplifying integrals with trigonometric substitutions and also with partial fractions. And then we're going to do one example of something called integrating over an arc, or finding the arc length of a curve. Now, that might not have been done in class before, but since it's going to be part of the final, I think it's important to at least see one example in class, and it's actually not too bad, okay? So, how's that sound? Quiet crowd today, that's okay. So we'll get started. So, Pari is playing an ultimate frisbee game. About to make a catch, Pari sees that the frisbee will fly through a small arc between the angles pi over 3 and pi over 6. Let's compute the total number of positions the frisbee can be in, i.e., let's compute this integral. So just a simple substitution here. We know it's going to be a substitution because we see functions that are composed inside of each other. And, well, let's try it out. Let's see what happens. So we have this ln of sine of theta. Let's try and make a substitution here. So if we set u to be equal to the ln of sine of theta, let's try taking this derivative. We'll get that du is equal to, remember we'll have 1 over sine theta from our ln rule, but also we have to remember to multiply by that chain rule. So we'll get a cosine of theta d theta. Would you look at that? du is just going to be, if we remember cosine of theta over sine of theta, that's just our cotangent of theta. So we'll have cotangent of theta d theta. So now we have everything left that we have to substitute here. So we've got our blue portion here, we've got our orange portion there. We'll substitute everything back. So in our next line, we'll have the integral of u du. And we have to remember to change these bounds. So in particular, when theta, we're integrating from theta equals pi over 3 up to theta equals pi over 6. So when theta equals pi over 3, we have that u is going to be equal to the ln of the sine of pi over 3. So sine of pi over 3, we'll remember that's root 3 over 2. So this is going to be the ln of root 3 over 2. Similarly, when theta is pi over 6, we're going to have that u is going to be the ln of sine, ln of sine of pi over 6, which is the ln of 1/2. So we're going to be integrating from u is equal to ln of root 3 over 2 up to u is equal to the ln of 1/2. So after we integrate, we're going to get 1/2 u squared evaluated from ln of root 3 over 2 up to ln of 1/2. And then this last evaluation step will just sub in. So this is 1/2 ln of 1/2 squared minus ln of root 3 over 2 squared. Okay, so a nice little warm-up just to get our feet wet, remind ourselves about u substitutions, particularly when our u is going to be equal to some trig functions. So when we're doing this substitution, we'll notice that we're still choosing u to be equal to something with a trig function in it. So this is still our regular u substitution. But we're going to see later where our trig substitutions are going to take a little bit of a different form. Anyone got any questions about this example before we go forward? Awesome. Let's keep going. So, partial fraction decomposition. Okay. Who's a fan of these? Yeah? I love the energy there. You can grab the candy cane afterwards, though. I don't know where they've gone on to. Okay. So, partial fraction decomp is actually a lot simpler than we might think. So we'll illustrate it with an example, and we'll kind of build upon those examples as we go forward. So let's compute the integral of 1 over x times x plus 1. What makes this integral tricky is that we don't have any techniques for evaluating directly what this fractional function is, right? So what partial fraction decomp tells us is that we should try and rewrite this fraction in two different fractions, right? Now, if those two parts were in the numerator, it would be pretty easy. We would expand them and then break them up, right? When they're in the denominator, it's a little bit more tricky because we can't just break them up. So what we're going to do is we're going to rewrite 1 over x times x plus 1 as some number a over x plus some number b over x plus 1. Basically, we're going to assume that this kind of decomposition is possible, right? And we know there's some theorem in the textbook that tells us that this is possible. So now all we have to do is solve for a and b. So this is step 1. Step 2, let's solve for a and b. So to solve for a and b, let's multiply both sides by x times x plus 1. And we know that this equation holds for every x. So what we're going to do is we're going to plug in values of x, which allow us to solve for a and b. So I'll note that down, that's really important. Assume that this holds. Assume this for every x. Now, if it holds for every x, then it definitely holds for example, x is equal to 0. So let's try setting x is equal to 0, and we get that 1 is equal to a times 0 plus 1 plus 0. Oh my gosh, that means we can solve for a now. That tells us that a is equal to 1. Now, let's also try and solve for b now. So if we want to solve for b, let's eliminate this x minus x plus 1 term. So let's set x to be equal to negative 1. Then our equation gives us that 1 is equal to a times 0 minus b. So b is equal to negative 1. Once we've solved for those two values, we can literally plug them back in as our components for this decomposition. So we literally just showed that 1 over x times x plus 1 is equal to 1 over x minus 1 over x plus 1. So we can now use that and sub it back into our integral to help us. So if we call this integral I, then in that case, I is going to be also equal to the integral from 0 to 5 of 1 over x minus 1 over x plus 1 dx. We can evaluate this by using our logarithm rules. So if we integrate, this is going to be the ln of the absolute value of x minus the ln of the absolute value of x plus 1 plus c. Oh, actually, let's evaluate it from 0 to 5. That's my mistake. Actually, this is a silly question because you can't take the ln of 0. So let's assume that we got rid of those bounds and we're just asked for the indefinite integral. So that's my mistake. We're looking for the indefinite integral. Aha. And it's ln of the absolute value of x minus ln of x plus 1 plus c. How does everyone feel about that partial fraction decomposition? Good. It's not too bad if you think about it like that, right? So let's try one more example. What questions do we have about this one? Yeah, go for it. If, sorry? Like if you chose different values for x, you still get 8. You would, okay. So this is a really good question. So the question was, if we chose different values for x, would it still give the same values of a and b? The answer to that is yes. The thing is, we wanted to choose these particular values of x in order to get rid of the other variables, right? If we chose x is equal to 2, then our equation would be like 1 plus 3, or 1 equals 3a plus 2b. That doesn't help us solve a or b. So what we're doing is we're trying to find and isolate those values of a and b. That's a good question. So we'll see this illustrated in the next example here. Let's find the integral of this expression here. The partial fraction decomp works the exact same way. For every single one of those terms in the denominator, let's rewrite. We'll have 1 over x times x plus 1 times x plus 2. We'll assume that is going to be equal to some number a over x plus some number b over x plus 1 plus some number c over x plus 2. So now let's solve for, actually let's rewrite this really quick. We'll rewrite this as 1 is equal to, so we'll multiply both sides by our denominators there to just make it easier. So 1 is equal to a times x plus 1 times x plus 2. B is going to be equal to, plus b times x plus 2 plus c times x times x plus 1. And now our goal is to solve for a, b, and c. Okay, so how are we going to do that? Let's say we wanted to solve for a first. Let's try and choose an x value which eliminates all of those b and c's, right? So if we're solving for a, remember this holds for every x. Let's choose x to be equal to 0. Someone got an email. If we choose x to be equal to 0, then all of those b and c terms with those x's are going to go away. So we'll have 1 is equal to a times 0 plus 1 times 0 plus 2. So that tells us that a is going to be equal to 1/2. So let's try and solve for b again, or solve for b now. So notice the a and c terms both have factors of x plus 1. So if we want to solve for b, let's set x to be equal to -1. That way it eliminates those a and c terms. So we'll get 1 is equal to b times -1 times -1 plus 2. So b is going to be equal to -1. Let's solve for c really quick, and then we'll check in to see where we're all at. So to solve for c, we could notice that a and b both have x plus 2 terms. So what we should do is we should try and eliminate those x plus 2 terms. So we'll set for c, we'll set x equal to -2. Then we have the equation 1 equals c times -2 times -2 plus 1. So c is also going to be equal to 1/2. Okay, we'll take a really quick pause now that we've solved for those coefficients. Is everyone okay with the idea of taking our big fractions, which have a bunch of multiplications down in the denominator, and separating out those terms into multiple other fractions, which are easier to integrate on their own. Or what questions do you have about that in particular? Yeah? How did we go from... Do you mean how did we go from this step to this step? Yeah, all we did was we multiplied by this denominator. We multiplied both sides by that. Awesome. What other questions do we have? By the way, if you're stuck on an early step, please just shout out and let me know, because it's better to understand every step as you go through it than to trace back to it. Yeah. Okay. Is this all good so far? So what we're going to do is we're going to take those coefficients. We know a is equal to 1/2, so we'll get 1/2 over x minus 1 over x plus 1 plus 1/2 over x plus 2. So these just come from our coefficients that we solved for. And now we're going to want to integrate this. So to integrate that, here I'll just write a dx on this side. So then here we can just use our logarithm rules. We'll get this as the 1/2 of ln of the absolute value of x minus the ln of x plus 1 plus 1/2 times the ln of x plus 2 plus c. And that's going to be our final answer. What questions do we have? Is this all good? Oh, why didn't I use the 5 and the 3? Oh, that's a good question. Sorry. Are we all comfortable with using the fundamental theorem to evaluate integrals at different points? Just for the purposes of saving time, let's just compute indefinite integrals for today. Yeah. Is that okay? Yeah. Do we have any other questions about what we've done so far? Oh, yes. Shout, you're loud. How do we know to put -1? To solve for b. That's a great question. So, what we're noticing here is this equation holds for every single x, right? So what we're doing is we want to find the value of x, which gets rid of everything else except b. So notice a and c both are multiplied by x plus 1, right? So if we set x to be equal to -1, that'll get rid of those a and c terms, and then we can solve for b. Does that make sense? Awesome. Okay, let's keep going. So, how do we do partial fraction decomp when we have a repeated root? So this one's a little bit of a tough one, okay? What we're going to do is we're going to make the assumption that this fraction can be written as okay, when you have a repeated root, all you do is you add an additional term with that higher powered root. But you need to make sure that you also keep the lower powered root. So for example, this is going to be decomposed into into a over x minus 6 plus b over x minus 2 plus c over x minus 2 squared. So for every time we have a higher ordered power, you need to add an additional root. add an addition, or sorry, not an additional root, add an additional fraction with a higher ordered power in the denominator. If it was x minus 2 cubed, we would add on a d over x minus 2 cubed, right? But you also need to include all the lower powers. So let's solve for this. So let's multiply both sides by the denominator. So we'll have 4 is equal to a times x minus 2 squared plus b times x minus 6 times x minus 2 plus c times x minus 6. Okay, let's try it. Let's solve for a. So if we wanted to solve for a, what value could we choose x to be? Just shout it out. 6, yes. That will eliminate the b and the c terms. So choose x equal to 6. Then 4 will be equal to a times 6 minus 2 squared. So a is equal to 1/4. Okay, what if we wanted to solve for b? What value could we choose x to be? I thought I would get you there. We can't do that yet. Let's do c first. We're going to solve for c first. Solve for... Here, we'll solve for c first. The reason why is because we're going to use our values for a and b to solve c later. So solve for c. What value could we choose x to be? 2. Very good. Thank you. So we'll choose x equal to 2. Then we'll have 4 equals to c times 2 minus 6. So c is going to be equal to -1. Okay. We'll take a quick pause. Is everyone okay with what we've done so far? Yeah, question. Yeah. A over x minus 6, b over x minus 2, c over x minus 2, b over x minus 2 cubed. Absolutely. That's absolutely fair. Okay, so let's solve for b now. So let's rewrite our equation with our new constants. So after we rewrite, we're going to get 4 is equal to 1/4 x minus 2 squared plus b times x minus 6 times x minus 2 minus 1 times x minus 6. So all we're doing is we're subbing in our values for a and c, and now we can solve for b. Okay, so let's solve for b. Let's just choose x to be equal to 2. Oh, no, sorry. Oh, no, we can't choose x to be either of those nice values. Let's choose x equal to 0. So if we choose x to be equal to 0, we get 4 is equal to 1/4 times 0 minus 2 squared plus b times -6 times -2 minus 0 minus 6. So if we run that, b should be equal to 1/4, right? Actually, I'm just going to check this online. Yeah, b is equal to -1/4. So now all we can do is let's sub those back into our integral. So we'll sub in our values for a, b, and c. So our integral is equal to 1/4 over x minus 6 minus 1/4 over x minus 2 minus 1 over x minus 2 squared. So let's try and integrate this. So if we try and integrate this, the left-hand term, that's going to be 1/4 over x minus 6. That's going to be the ln of the absolute value of x minus 6. This is going to be -1/4 times the ln of x minus 2. And then how do we use that last one? That's not a log rule, is it? No, that's a power rule. Power rule, right? So we have a negative 2 in the power. So hold on, let's just rewrite this to the side. So this is equal to negative x minus 2 to the negative 1. So we'll add 1 to the power, and then we'll divide by negative 1. So this is negative x minus 2 to the negative 1, and this becomes a positive. And what did I forget? C. Plus c, very good. Jessica.
Why is it 1 over 4 multiplied by 6 minus 8?
Oh, very good catch. Thank you. There should be a 1/4 here. Great catch. Yeah. Oh, scroll back down to this side? Yeah, of course. How's this? Awesome, my pleasure. Yeah, go ahead, take a picture. Yeah.
Sir, could that last term be to the power -2 instead of to the -1?
This last term, I think it should be to the negative 1. Right now it's a power of 2, right? So after we get the power rule, we want to add 1 to the power, yeah. All right. Okay, what questions do we have? Still here a lot of numbers. This all good? All right, let's keep going, let's keep going. So, the good thing is, partial fractions doesn't just work on integrals. So, let's compute this sum. Yeah. Oh, that was just an, okay, this is a good question. Why did we pick x is equal to 0 for this example? It's arbitrary. This equation works for every x, and unfortunately, if we chose 2 or 6, that would eliminate b, right? The problem is b is attached to those cross terms. So all we have to do is just plug in some random number, and I thought 0 is the easiest. That's a great question. Do you want a candy cane? You want a candy cane? I'll take one. Anyone who's asked a question, by the way, feel free to come grab one. Just pass them around. Here you go. All right, so let's use our partial fractions to evaluate this sum. Let's do it really quick. So let's factor this rational expression. This is 1 over n squared plus 3n plus 2. We're going to factor that as 1 over n plus 2 times n plus 1. Aha! What do we notice about that? We can apply partial fractions to this. Okay, so let's apply our partial fractions. So, actually, did we solve, we might have solved n plus 2 over n plus 1 before. Oh no, we did x and x plus 1. Okay, so we got to redo this one from scratch. So this is going to be equal to a over n plus 2 plus b over n plus 1. So if we solve, this is going to give us 1 is equal to a times n plus 1 plus b times n plus 2. Okay, so to solve a, we set n equal to negative 1. Or sorry, to solve for a, we set n equal to negative 2. So that gives us 1 is equal to a times negative 2 plus 1. So a is equal to negative 1. And then if we want to solve for b, we can set n is equal to negative 1 to eliminate a. So then b is equal to, 1 is equal to b times negative 1 plus 2. So b is equal to 1. Is this step okay? So we're just using our partial fractions ecomp, and then we're eliminating each of those terms. Then, this sum is now going to be turning into, we'll have the sum from n is equal to 0 to infinity of, we have negative 1. Actually, I'm going to write the b term first. So we're going to have 1 over n plus 1 minus 1 over n plus 2. Okay. This should be really, really great prep for the final. What kind of series is this? Telescoping, right? We're eliminating every term, so let's actually try this out. So this, if we write out the first few terms of this sum, this is going to be 1 over 0 plus 1 minus 1 over 0 plus 2 plus 1 over 1 plus 1 minus 1 over 1 plus 2 plus dot dot dot, right? Okay, this is minus 1/2, this is plus 1/2. So this is canceling, and this is going to keep canceling forever. So that entire sum is just equal to 1. It's going to keep canceling forever. No, because we're going to infinity. So this is such a satisfying answer, right? We had this really brutal question, but we got it down, and it's literally just the number of 1. You're so sweet. You guys are number 1. All right. This is terribly evil. Skip this. And we'll come back, maybe. Okay. Everyone's favorite, trig substitutions. Right? Everyone's favorite? No? Okay. This will be very helpful. So the following table will be helpful for integrating by trig substitutions. Memorize this table. Just do it. Just memorize it. Okay? Now, you've all seen the first 3, or you should have. Some classes might not have seen the last 2. Have you seen the last 2? Who has? We skipped over it? All right, then we'll have one example to at least see what the second 2 are. But memorize this table. Jessica. So, this is supposed to be a hint that shouldn't be there. Okay, so Jessica is saving up money to attend a Stray Kids concert. The concert tickets cost sinh inverse of x minus 3, or x over $3, and Jessica has the log of the root of x plus 9 over 3 plus x over $3. Let's prove that Jessica can afford to buy a ticket. That is, let's prove that the sinh inverse of x over 3 is equal to the log of the root of x squared plus 9 over 3 plus x over 3. Okay. This is a really good question. I promise there won't be anything on the file that's this tricky. They won't ask you to prove something. But it's good for class. So here's the trick. Here's the trick, okay? We're going to look at the integral of 1 over the root of x squared plus 9 dx. This is the trick. How would you know to do this? You wouldn't. I purposely made this question like brutal. But we're going to look at this integral, and we're going to do it using 2 different types of substitutions. One of them, we're going to use here's what we're going to use. One of them, we're going to use the root of x squared plus a squared trick, and that's going to turn into, we'll have we'll use the substitution x is equal to a tan of theta. And we're also going to use the substitution x is equal to a sinh of t. We're going to try it both ways, and we're going to compare the answer. And when we see that those 2 answers are the same, we'll know that those 2 things are supposed to be the same, because they're both equal to the integral. So let's try it. So let's try it using our regular trig sub. This one's the important one to pay attention to. So this is going to be equal to, if we set x to be equal to, now let's rewrite. This 9, that's the same thing as 3 squared, right? I'm just going to rewrite that as 3 squared. So if we use a trig sub, let's set x to be equal to 3 tan of theta. Notice this is different from our normal trig subs, our normal u subs. Because normally we're setting u to be a function of the variable we used to have. Right now, we're setting our current variable to a function of the new variables. So notice it's a little bit different. So after we do that trig sub, we're going to have the integral of 1 over the root of 3 squared tan squared of theta plus 3 squared. We also need to sub in the dx. So if we isolate, we have dx is equal to 3. What's the derivative of tan of theta? Secant squared, nice. D theta. So this is going to be 3 secant squared theta d theta. Nice. So let's keep going with this integral. So here our 3 is, if we pull out these 3 squareds, they're going to cancel with our 3. So we'll have 3 secant squared of theta. We'll pull out these. We'll have 3 times the root of tan squared theta plus 1. Wait, tan squared theta plus 1, that's just secant of theta, right? Or sorry, the root is just secant of theta. Good, is that what you're going to say? Yeah, good catch. So here, and our 3's will cancel. So this is just the integral of secant theta d theta. Okay, do we remember what the integral of secant theta d theta is? That was a tough one, eh? Oh, you got it? So, hold on. So, ln of secant theta, yes. Plus tan, oh yeah, you got it. Absolute values. So this is the ln of secant of theta plus tan of theta. Plus c. Well done. That's very good. If you don't remember that, go back and remember that. Okay, so let's substitute our thetas back in. So this is now, if x is 3 tan theta, that means now we have the ln of, let's substitute back our tan theta first. So our tan theta is x over 3. And our secant theta, in order to substitute back for our secant theta, we'll just take a look at, so let's look at x squared again. So x squared, or actually we said it right here. X squared plus 3 squared rooted, that's secant of theta. So this is just down, I'm just taking that from this step here. So we have 3 secant of theta is root of x squared plus 3 squared. So we can just sub that back in for our secant of theta. So we'll have root of x squared plus 3 squared over 3. Okay, so that's, look, that's the right-hand side, right? That's the right-hand side. So if we can show that that integral that we just computed, if that integral is also equal to the left-hand side, then we know that the left and right-hand side have to be equal, right? Are we totally lost here? Yes? Okay, so basically, we want to prove that these two things are equal to each other, right? We want to show this. So if we can show that the integral of this guy, if we can show the integral of this is equal to the left and also is equal to the right in 2 different ways, then we know that those 2 things are equal, right? So we did one integral in order to get the thing on the right-hand side. We're going to do a second integral now to get the thing on the left. Is that cool? Awesome. Yes, question. Why did we know that it was the integral of that function? You wouldn't. I made this example just to teach how we can do multiple different types of things. So if you're curious as to how this integral even came up, don't worry about that. They'll give you that integral on the test. Okay? Okay, let's try a hyperbolic sum. Let's try one really quick. So, we're integrating 1 over the root of x squared plus 3 squared dx. All right, so we're integrating this function. We're going to use the substitution x is equal to 3 sinh of t. Then let's take the derivative. We'll get dx is, that's the same color here. Wait, we'll get dx is equal to 3 cosh of t dt. So let's substitute back in. So here, this will be the integral of 3 cosh of t dt, all divided by, now if we're taking the root of 3 squared sinh squared t plus 3 squared, same thing's going to happen. Those 3's are going to cancel, so we'll have 3 over 3, and we'll have the root of sinh squared t plus 1 over cosh of t dt. Wait, what's sinh squared of t plus 1 rooted? What's the root of sinh squared plus 1? Cosh, yeah. So remember, this is the integral of cosh of t over cosh of t dt. Also, by the way, let's talk about this identity that we're using here. So we have the identity sinh squared of t plus 1 is equal to cosh squared of t. Okay, notice, it's important. This identity, you can tell, is different from the regular cosine and sine, right? Because normally we have sine squared plus cos squared is equal to 1, right? For sinh and cosh, it's in the wrong place. The 1 and the cosine switch places. It's very weird. But we just have to work with that. So this is going to be, it's the integral of cosh t over cosh t. It's just going to be the integral of dt, which is just t plus c, which is equal to, remember, if t is, here, t is equal to, if we sub this back in, t is going to be the sinh inverse of x over 3. Okay, so what did we show? We computed that blue integral in 2 different ways. We know integrals are unique, right? Other than a constant going up or down. And we showed that if we integrate it using a regular trig sum, we'll get the ln of that number on the right-hand side. And if we integrate using a hyperbolic trig sum, then we get the sinh inverse of x over 3 plus c. And we have the whole, we have plus c on the whole part. You would have to show c is equal to 0, but that's fine. That doesn't matter. Yeah?
Can you explain how we got from the integral of secant theta to ln secant theta?
So all we did was we literally just integrated here. So we're just using the integral of secant of theta, d theta, or secant of t. You should remember the integral of secant. You won't have enough time to derive that on a test. Any of those, like secondary trig, like if you're integrating secant, integrating cotangent, you won't have time to do it on a test. Remember that, okay? Okay, oh yeah, one more question, yeah. Oh, okay, so here's I'll give us the kicker. This is the kicker. So we just showed, so we're integrating 1 over the root of x squared plus 9 dx, right? That was what we integrated. We showed in blue, we showed that that's equal to this, right? And in red, we showed that it's equal to this. So this is the kicker. This is the moral of the story. We computed that the integral is equal to the left, and we also showed the integral is equal to the right. So those two things have to be equal as well. So we showed, right? The integral of this. We just showed the integral of this is equal to this expression here, right? It's this. Is that okay? Well, let's talk more about that. Okay. All right, let's keep moving. We have only, yeah, so that was this. That was up that. Okay, we have not too much more time left. This is another partial fractions example. Try that on your own. Let's make that for homework for now. This is another, Let's see if we can come back to this one too. I really want to get to this last example. So we're going to let f be a function. The arc length, s, of the function from t is equal to a up to t is equal to b is given by this integral. So what does an arc length mean? Arc length means, okay, look at some function. I want to see how long that function actually is. What is the distance that that function covers, right? So the arc length is given by this integral. The reason why this integral makes sense is because we're comparing the speeds. Really what we want to do is we want to integrate the net speed of the function over the entire interval. So we're basically just breaking it down component-wise to the speed in x, the speed in y, and then using Pythagorean theorem, and then integrate. Okay, let's do this on an actual example. So we've been giving out candy canes. There's some candy canes everywhere, if anyone wants any, but the hook of the candy cane is traced by the function y is equal to the root of 4 minus x squared on the interval 0 to 2. The question asks, what is the length of the candy cane? That's a great question. So let's see what we need. We want to find s. In order to find s, what we need to do is break it down into each of these different pieces. So first off, let's find y prime. So this is y prime. Our function is, so hold on. Our function is 4 minus x squared to the 1/2. So this is good practice for taking derivatives. So we're going to have 1/2 times 4 minus x squared to the negative 1/2 times our chain rule, which is negative 2x. So if we rewrite this expression, we'll have negative x over the root of 4 minus x squared. Is everyone comfortable with that for our y prime? So then in order to find s, what we need to do is we need to compute the integral from a is 0 and b is 2 of the root of 1 plus the square of that. Dx. So if we integrate this, I'm just going to rewrite it a little bit cleaner. So we have our x squared, and we'll have 1 plus x squared over 4 minus x squared dx. Okay, we've got 1 minute. Let's try and finish this integral really quick. So let's rewrite everything inside the root. We'll combine it into its own fraction. So we'll have 4 minus x squared over 4 minus x squared plus x squared over 4 minus x squared dx. So this will give us the integral from 0 to 2 of, let's separate this root. We'll have the root of 4 over the root of 4 minus x squared dx. So this is 2 times the integral from 0 to 2 of 1 over the root of 4 minus x squared dx. Okay, what is that? What is that the derivative of? Ooh, tricky one. Yeah, what you got? Yeah, this is the arc sign. So this is, well, it's a modified arc sign because normally we would need this to be a 1, right? So let's do a really quick substitution. Let's set x to be equal to, let's do this. Let's use our Triggs substitution table. So let's just go back up really quick. So if we use this table, we know we have an a squared minus x squared. So we'll set x to be equal to a sine of theta. So here, let's set x equal to 2 sine of theta. Then dx will be equal to 2 cosine of theta d theta. We'll substitute this in. This is 2 over the integral from, we're going to have to change the bounds, but we'll have the root of 4 minus 4 sine squared of theta. We'll have 2 cosine of theta d theta. Look, our denominator, we also have 2 cosine of theta, right? Our denominator, we could rewrite that as 2 root of 1 minus sine squared of theta. We have, oh, I pulled an extra, sorry. There's an extra 2 here. This is 2 cosine of theta d theta. The cosines are going to cancel. We're just integrating d theta. So that's just theta plus c, and then substitute back in. Okay. Yes, quick question. Ah, that was my mistake. So I'm just going to put the 2 back in. That's my bad. But I shouldn't have pulled it out in the first place because it's going to cancel with something else. That's my bad. Anyways, I know we were kind of rushed a little bit at the end. Hey, thank you all so much for making this a wonderful semester. I had so much fun with you guys. I'll try and put out some extra study and stuff for the final. If you have any questions, as always, please feel free to reach out. I'm happy to help, whether it's class related or not. And best of luck for finals, guys. Have a good one.